My name is Ravi Sahu. I'm the founder and CEO of STRAYOS. My background is in the enterprise software for about 12 years. Before I started STRAYOS company, and what we do in STRAYOS over the last 6 years, this company is helping develop AI solutions for the mining industry, which I will cover more on what specific things are. But today I want to thank WAIMM for opportunity to present the latest topics and research that we have done for the industry. So I am thankful for the opportunity to interact with you all here. In between, if you have any questions, feel free to send it over the chat button here, as you have the ability to ask questions, or feel free to also ask directly with your audio as well. So today's topic is using AI prediction models for scenario analysis of drill and blast outcomes. The agenda is I want to set the context first, a little bit of an overview what we will going to talk about. And then you start with why AI models are becoming more and more important for drilling and blasting operations, and how we can leverage them better properly. And then what benefits and gains we can get from that. So these are the three ways that we will see today's session. A little bit more. I wanted to give an overview of where I work. So it's STRAYOS is a software company which is used in roughly 25 countries right now, in more than 3,000 mines, over 100 customers. Just what the solutions we cover is ranging from overall mine to mill value chain, to start from surveying and planning, where you can process the survey data and do a geology analysis automatically through AI. Then drilling and blast planning and loading and hauling analysis. And then the processing, which is the how the rock is on the grounds of fragmentation. And then overall modeling for your mine to mill value chain. And then on the crushing and the hauling side, we have solutions where camera systems can be installed at different places to do real-time analysis at trucks, shovels, crushers, and conveyors here to do various types of decision making, throughout the process here. So that's just a quick introduction here. I'm going to go directly into the topic here. So why the AI model helps, right? So in order to start with the AI models, we need a good data. And when the data is good, we can use that data to further augment various types of feedback mechanism. So the feedback mechanism could be you're starting with a design data, and then what's the outcome will be from that design. Now we can use that outcome to train the model for the next design. So if you have done it repeatedly for about 10 designs, now you have like really rich data that you can use to predict future outcomes. And that's what we're going to talk about today. So agenda, a quick introduction about more topic. What is this AI feedback loop? We saw that in the last slide more, but we're going to cover more in detail. And then we will going to look at very specific use cases, because you being on the engineering side and the industry side, the use cases is more important rather than just talking about the AI models here. So we're going to look into how we can improve the fragmentation in the mines of your blast. If you have strip mining operations, how you can improve the cost, and then how you can improve the dilution if you are focused on the copper mine, gold mines, more metal mines. And then also we will look at how you can improve the hauling and crushing side as well through the data that you generate and where the AI prediction models could be useful there. So the question that always comes, why we should use AI, why the transition to AI should happen, and why we should be looking at more closely, that should be our first question. So let's understand that why we should be looking into AI, why not just apply our empirical methods that has been working over the last several decades, why just not to rely on them and continue to do our operations. So one of the biggest benefit that I see is, as it's summarized in this slide, is AI is nothing but it involves the programming of the algorithms, which has been, let's say, your empirical algorithms, but it mimics the human thinking and learning on the problem solving. And then you have lots of data to scale that thinking exponentially and find patterns, right? So these algorithms not only can be programmed with a specific data set, but now we can develop the pattern recognition that usually it's harder to see in these empirical methods or just one set of algorithms. And then we can use those patterns to make new predictions. What if we see a different type of data? So what the scenario will be on those cases. Now, these algorithms can be trained again and again with a new set of data, new set of desired outcomes can be seen. And then we can test every possible scenario that is not been covered in the current empirical methods. So identifying different combination. But one of the beauty is why, because it can do that at a speed of milliseconds, right? So you have millions of records. Now you can run that when you train the AI models you can use this to see the different scenarios within a very fast amount time. And that's what the transition to AI should happen. That's why the question that comes is why we should be thinking about applying AI in the drilling and blast. So this is a code that I like because like how Thomas Edison kind of found 2,000 ways of how not to make a light bulb, right? Which is also very important, but only you need one to make it work. So that the same thinking and same approach, if we see it in AI, what one scenario works properly. And if you find that, we can accomplish in a second rather than like several hours or years of the data that we have not seen before. But before we switch to AI, the organizations also needs to think what they have currently, right? Because mines generate data every day from different sources. You have data, what we call computer vision data, which is data that's collected from sources like different imagery sensors, such as drones, which is cameras, LiDAR, scans, you have satellites, you have phones that you're collecting the photos as well. You have hyperspectral data and thermal as well. Now, those are all imagery, which means visual data. Then you have machine sensor data, which your machines are collecting, such as haul trucks, drill machines, or dozers. Truck data, you have lots of IoT data. There are sensors been installed in different parts of the mines, any type of equipment. Then you have the spatial data, which is coming from the GPS networks, RTX, networks here. And then also there are other types of data, geophysics, electromagnetic data that some of the mines collect. But why this is important, if you have a data, how do you can apply or different types of data that was not possible before? But AI gives you an option to apply this data and structure it all the multivariable scenarios, different types of scenarios that usually not possible in building one equation that only works for only one specific types of data input. So again, the context here is why we should think about the AI models here. And this is something that kind of you can develop an understanding, like our human brains are not good in retaining the information over a long period of time, but the human brains are really good in generating new ideas. So the same, if we think in terms of the AI model, we can automate a lot of the tasks in the form of the model development, which are more repetitive and more kind of information heavy. And then as a human, we can come up with new ideas to train the model. Now look at the challenge that you see in the organizations right now, right? Because in order to have a successful AI implementation or kind of building the prediction models, also need a structure in the organization, which most of the time, this can be categorized into these three buckets. So some mines kind of can fall into standalone systems, some are half integrated, some are unified. And the journey can be started in, can be anywhere in between here, but just going through is like, what are the standalone systems right now? Most of the organizations that we see is you have a resource planning tool, another system, you have mine planning systems, GMP packages, then surveying is something, somewhere else, and then you have IoT data. So all these are like very, very separate systems. They don't talk to each other. Then you have organizations which are, some of the systems are half integrated, where your resource plan talks to the mine plan. So it's frequently getting updated. Mine plan can talk to surveying, and then surveying is talking to only the data that's been collected from the site through these sensors. But again, these are not talking fully to each other. So the future vision is how we can bring these unified platforms, together, where AI can be even more useful. Is you have a resource planning that talks real time, or as soon as your resource plan is kind of changing or getting newly updated, it talks to the mine plan, geology modeling, and surveying systems all together, and everything is in sync. And any type of the other data collection which is there, that also gets fed back to these systems as well. So when we are in the unified platforms, the value of the AI can be seen a lot more faster here. So going from disparate data sources here to unified systems is a lot more appealing use cases for the AI. So machine learning and AI can bridge the data silos. That's what that whole premise is. Not only that, it can help generate contextual intelligence, which means it's not about what we are looking or what you're trying to solve, but also why you're trying to solve, right? Why you need it. So the question of why can be understood very easily. It can add a context to it. Then going from complex enterprise to streamlined enterprise. For an example here, I will go more in detail later, but if you have a problem of in the drilling side, and that what needs to be done, but there could be scenarios like why it is occurring, that problem. But there could be 5 different reasons, and we only know one of them. But the rest 4 could be even more impactful that we have not seen. And that contextual intelligence can be added once we start seeing the data and the outputs. So let's start really talking more concrete here now, how we can apply this, applying in drilling and blasting scenarios, right? So blasting has a huge, you may have seen this chart in many in other presentations or in your coursework. Blastings have a huge impact downstream, which means the total cost if our blasting operations have not been executed as desired, the cost goes significantly for loading, hauling, and crushing. So the cost is essentially how it determines what's the blasting results are, and the cost of the downstream goes kind of, up and down based on that. So usually we want to balance it, at an optimum point, as you can see here, where the total cost is like reasonably same what we are looking at, and it meets, properly as the desired scenarios. But in the blasting, you usually have certain things that you can control, which is you can control what type of drill diameter you're going to use, how you're going to drill at a specific depth. You have a control on the charging length, spacing, and burden design parameters, how you're going to design that you can continue to with that. Then, how to stem that, like at a specific length. You can control your powder factor. You can control the strength and the energy, the type of explosive you can experiment to change. You can control like how you're going to time it and how you're going to prime it. But these are all the controllable parameters. But what is not controllable is which we don't know. In that case, the rock strength, the gravity of the specific rock, the spacing, joint spacing conditions that exist. I heard noise. If there is any questions, feel free to raise hands and ask. Then you have you don't know the presence of water as well in those specific whole column. We don't know the stress wave velocity, how it's going to behave there. So this what blaster cannot account for. You just know it, but you don't know what the behavior will be. So when we utilize AI from the historical data to predict this, now we can kind of unlock various powerful scenario outcomes through this feedback loop of training, which means we have the input data in a form of design, which is our burden spacing, pattern layout, explosive selection. You have QA/QC data, drilling accuracy that you have done. So you're collecting all those loading data. And then the contextual data, which is if you have done the rock mass analysis, or if you have drilling data in form of measure while drilling, if you have a very specific ore zone analysis that you have in terms of blast movement. Now you can have a performance data as well after the blast is done, such as fragmentation, movement, or vibration. And then the downstream data, such as how the machines are performing, which is diggability, crusher throughput, yield at the plant, and then the overall cost data can also be incorporated here. Like, so what is the overall cost of this drill and blast? Now, if you have this data, and if you have 5 or 10 blasts, so the areas that we can't account for earlier, let's say we can do a design and hope that the behavior will be the same. But if we have this data for 5 or 10 blasts, and we now train a model, and now we use the same parameter to see how it will behave for the next drilling condition or blasting condition for the same type of rock that we have. What was the result after that? So now we know the scenarios that could occur. And we can change that scenario, like let's say we want to change maybe explosives, or maybe a pattern here, maybe make a pattern bigger and see what the outcome could be. What's the overall cost, could impact here. So this is where the feedback loop, can come in very effective when you have a data that you can use to train from the historical models. Then on the fragmentation prediction, the another balancing act is, for the fragmentation is, if you have too much powder factor, you can do a very finer fragmentation. You can generate a lot of fines. But if you don't, then you have decreased kind of the throughput rate, which means you are using the secondary breakage to break those rocks. So again, this is a balancing act. And then the loss that occurs, which means from the fines, you have too much dilution and you throw away that material. That's just the overall loss to the production. So again, the fragmentation is a key thing here. What if we could predict a really better fragmentation based on the drill blast design, and then also everything from the geology side, and it can help us get to a desired fragmentation size. So, and then we can balance our outcomes here. So that's another use case. So the measured size distribution that you are trying to predict should match the optimal feed that crusher takes, right? So that's always the goal, that if our goal is for the crusher is to take 27-inch particle size, so we should be only producing those kind of, rock particles, and what's the pattern and what's the overall explosives condition we should be applying to get to that particle size. We may not get there 100%, but what if we could get 80% of those size criteria we meet? That means that's a desired outcome that we are looking for the crusher then. So how we can kind of apply this, right? So I want to go into a little bit more technical here now. So if we use the deep learning neural network, which means if we train the architecture where we have lots of data, which we will call here, in this case, we have trained a multi-layer artificial neural network, which has 4 hidden layers. And there are what we call hyperparameters, which are used to tune what's the outcome we want. And if we adjust the tolerance of, like, if we kind of increase the tolerance that I want a more improved results on the true positives, right? So that tolerance can be controlled, which we call the number of neurons that you need in each instance. And there are several ways to kind of achieve it. There is different models out there that you can apply. You can iterate these models by adding more neurons. And then also it can be very computation heavy in the beginning when you are training the model. So there is always an approach of iteration is required. How to build a model, but also how you can apply it at a level where you can use it for again and again. So the model is trained with a multivariable network here, and then we can apply these different parameters that I talked from the very beginning, how the feedback loop can work. So from the fragmentation prediction side, this especially covers, we trained a model which is have 4 hidden layers, which looks at the different scenarios here. As you can see, this is bench height, spacing, burden distribution, depth, powder factor, energy, and then this was all the input layer. And then it predicted the output layer, what's the particle size 50 will be. So that was the model here. And then as you can see, it predicted based on different number of blasts, where we have like all this data, where we saw the prediction and then the actual, because the actual data was also collected for this, all this blast. So we saw that the actuals that was there and what's the prediction was there, that was relatively, there was a distribution here. So we can see it is kind of quite matching in certain scenarios. The star, there is like a spike here, but that relates to kind of, how some of the blasts, maybe your geology kind of, varied hugely, one of the blasts. So that also gives a quick indicator, what are those scenarios that didn't match, and we have a prediction and actual didn't match there. So now you can start to build a hypothesis about how to understand the data that has been done from the actuals and the prediction here. Because we can't rely just blindly on the prediction, that we need to understand what data went through in predicting those as well. So now this was the actual versus predicted value. As you can see, looking at the comparative assessment of the actual, we trained 3 types of model. One is the artificial neural network, one is the just the empirical base, which is the QuizRAM here, and then the SVR, which is the SWIB rate here. So now the same blast, what we're comparing with the traditional methods and the AI-based methods here. What we found is QuizRAM has the highest mean square errors that in terms of what the actual and the predicted was. So we saw that the neural network, because there was a lot more variables from the data side, multi kind of parameters, it uses data to kind of get to a lot more clarity on the or closer to the actual parameters here. Applying it to the real example here, what we saw, we were able to see this is an actual scenario in a coal mine where a pattern that was used to predict a new pattern based on what the data that they have, they were used to drill 107 holes at 20 meters. Now, after the AI predicted, we saw that the same outcome could be achieved with 87 holes at 16 to 18 meter field depth. Yeah, there is a question. All right. So in terms of the pattern optimization, the same outcome could be achieved with 87 holes that the new pattern prediction that happened. We took at the ideal design that was there with their bench, and then the as drilled. We didn't change any type of explosives here, but just on the drilling side, once the pattern was optimized, there was 20% less drilling was needed, which obviously saved the cost, and that just straight forward changes that was the outcome was generated from here. So the extra holes at the edges were optimized, obviously, that created much more better fragmentation than which they were not getting before. And I can see in the timing prediction analysis here, in the previous one, there were a cluster of holes firing together at 25 milliseconds, which resulted into wasted energy. So the AI kind of predicted those areas as well that to be changed to get a better burden relief or energy relief on those areas as well. So why these examples are important is if you can trap this, if you can catch this when you are actually designing things, now we have a good understanding of what kind of outcomes we can see. And that's the whole goal of this presentation today. Like, can we spot this based on what we have seen before? So now the prediction side, if we can see what's the actual measurement was in some of those previous historical shot and what we can now predict based on new pattern. So new pattern, if it is predicting 25, in this case, the new pattern predicted 24% more material measured in what the size range that they were looking. So that's again an ideal scenario that if I am getting 24% more material in the category that I want, that I was not getting before in that other pattern, it's a win for me then. So overall, there were the downstream obviously changes were there. So the AI model kind of not only automatically measured the fragmentation, but also predicted impact of what the design change that we are doing, what the impact will be. And then also certain changes on the explosives can be experimented. Like, if I'm only doing N4, or can I do a 30% blend? What's my size distribution would look like here? So it is predicting if I am using 30% blend, am I getting certain kind of variance on the size here? So these all scenarios can help me in making more better decisions for the drilling and blasting outcomes that I am looking for. Now, looking at the another use case, same thing on the drilling and blast, but more specific to the strip mines, cost. cost is a big lever to reduce a strip mining cost, right? So, we always want to move the overburden as fast as possible with the cheapest cost, and then get to our, seam to get the, ore body out, from that block. But more material we can cast, that means, less rehandling, which means less equipment, cost, reduce, equipment wear and tear, but also we can increase our production capacity faster, in that case. And overall, there is also a reduction in the energy, fuel, and the consumption because we are getting, to the ore body faster here. So how do we achieve that? So there are two ways, there are two key things in the cast metrics to measure. One is the cost percentage and the center of mass movement. The cast percentage is, these are all geometrical parameters. So now I'm moving towards, earlier we were talking about how we can do the parent designs and use all the explosives data and then the historical data to model and train a neural network. Now we're going to look at how we can train the geometry and the shape in the neural network to predict the movement here of the cost, or the percentage of the cost that we are looking. So in terms of the cost percentage, it's essentially, it's good to understand a little definition here. It's the proportion of material that was thrown to its final position in the wall, what we call kind of the lower side of the wall, which we usually call the spoil pile, or the pile that we will not touch, that will just stay as it is, and we're gonna straight go to move the material that we need. And then the center of mass movement, which is the center, or the kind of the distance that the shot will move here from the design to the actual post blast, how much it has moved, which means essentially how far the material has moved. So how do we use the cost blasting, or kind of how to run the cost optimization using AI? For that, it is necessary to go with few different steps, and that's how we have laid out here is you will prepare, the preparation is very necessary for the team here, which means you will align on a plan with blast crew, engineers, and production. You set up, different tools that you have, whether you're doing a scanning with the drone or other types of software. You do a baseline of like at least 5 shots, both pre and the post blast. Then you model those into software where you have where you're seeing what cost percentage you are getting, and then what's the center of mass movement is for all these post blast scenarios. Now you have the data baseline scenarios established, which means pre-blast is there and post-blast is there. Now adjusting for the next set that you're trying to predict, which will be aligning on what target cost profile that you are looking. So if your goal is to consider, if you have a drag line pad that you're considering, which has a specific angle it digs and moves the material, and that's your target profile, which means let's say a 40-degree, 45 or 30-degree, then you can align those as a outcome scenario. In the previous example, we were looking at what particle size we are trying to accomplish. Here, we're looking at what profile or the cost percentage or the angle that we want. So in this case, now you can start using the data to test what timing and products age that is required to get to that profile line, and then maybe design needs to be adjusted. So you can use that data to again do a feedback loop and track performance to run this cost optimization. So this is again a real world example where the cost predictions are used to predict 3% more cost after making the design changes, where you are looking at different scenarios of the movement, and how it can impact is with just a few set of improvements, of cost improvement of 2%, it could lead up to the overall production rate improvement, like, load cycle, per hour, can be improved, which has a, the cost reduction that you can get these benefits, overall as well. So not just looking at what the percentage, what percentage of cost that you will get, but also what downstream, improvement from the loading side, you can get as well. The third example I want to talk about is the dilution control from a metal mines, perspective here. So dilution control is a big factor when we are thinking into metal mines perspective, because we want to reduce the ore loss as much as possible and control the waste, there, and improve not only the production, but also improve the quality of the production here. So how can AI be useful here? I want to come back to this neural network training later, but what is the dilution here? Essentially, when we have a blast design, we have a timing and everything. It moves the material, and we don't want the waste to move, mix with the actual ore to dilute the overall, production value there. So what if we blast in a certain way where we can clearly move the waste and only focus on the ore to move that, to the plant. So clearly separating the waste boundaries. So what type of timing parameters we could use, what type of explosives to be used, or what's the design changes we can use to get there, right? So the idea here is how this neural network was trained. From the prediction side, you have input image file, which means, again, either is taken from pre-blast photos, which is drone photos, and then we use that data to analyze each segment of that map or the 3D model to feed that every 5 centimeter by 5 centimeter grid. It's been broken down into patches, and then it's been fed into the model, and it generates a new segmentation map, how that dilution will look like in that same map based on all the design parameters that we have. So let's look at how it works. So you have input data, which is your drone generated digital elevation model, which has a certain pixel value associated with every centimeter. And then you have the orthographic image, which is what we call orthophoto. And then you can have your area of interest or region where you're blasting, and you put your design data, your design parameters, timing, loading, all types of information, your rock material properties, which means if it's a copper, what's the rock density, rock mechanics information, and then obviously you design and load the shot. And then you have a block model that you can incorporate, because that will have a resource distribution for that same area that we can model to predict how these resources will move for that block. So what it does is, now this neural network we saw here, with all this data as a combination, it predicts a new type of surface. It generates a new surface which shows, as you can see, this is just a pre-blast, but now we can see how this is a pre-blast, and you can see this pixel by pixel information. Now it's been used to predict a new type of surface, from this, and how it will look like. And it is predicting the image-based predictions here. And what it tells that now, we can, if we have the block model data, we can see like where the waste kind of moved, where the ore moved, or how it's mixed together. So essentially, it's an iterative deep learning kind of, what we call solver that helps move each dynamic particle every 5 centimeter block, and it has the position in that specific time period. So this model, not only it's a spatial, but also it's like, you can incorporate the time series data as well. So just a quick demonstration here. As you can see, you have the model to get a better perspective. You have the area of interest, and you have the pattern. You put your timing loading data, and then you put your block model here, which are the different resources at specific positions, which are geospatially aligned. So now we go and predict a new surface, from that after the AI model is run. So this is a new surface that is getting generated before you go and blast this, how it will look like. So now if we have that, now we can simulate from combining with the resource model to see where the different resource blocks, each color means different type of resources in that block. So we can estimate how it's going to behave. So if it's not behaving as we want, we go back and change the designs, and then also make sure that what we are want to achieve here, we can iterate on those parameters here. So again, prediction and the outcome. The last one that I want to talk about is the crushing and hauling here, how we can use the models to better understand the crushing and hauling. So for that, it is important to collect the data at crushing and hauling site. And the way you can collect this data is you have the data capture tools that you can apply with this could be as camera systems, which can be installed in different places at crushers, conveyors, shovels, or gantries, where the truck is passing as soon as the material is loaded. And then you have the edge AI, what we call the AI is running as it's seeing the data real time. So AI can monitor and predict the ore content at different stages of crushing and screening. We can eliminate the low-grade waste, which means that needs to go to the waste pile, or the oversized rock is coming. So we can kind of predict that as well before it comes to the crusher. But now we have that data is processed real time. How can we apply into the process intelligence of crushing and hauling and feed back to the blast modeling? So the process intelligence, you have the data for exact kind of different places where you're monitoring the rock particles, volume, and then also the ore grade, here. So that leads to different type of understanding because now I have the data not only from the drilling and blasting, but also how that data is being used in the crushing side, because everything revolves together, and it's a feedback loop. Now we can use this data, what's happening in the plant, to make more better decisions for our drill and blast outcomes here. So let's just quickly see. So you have the data where you're continuously seeing and have a good understanding of what we blasted and how it is behaving in the plant. You can see every timestamp, like every second, how the rock is crushed, how at the primary, at the secondary, all this information that you have. And you can see this is kind of the real time where it is like, on the moving belt, you are looking at the different rock that's been predicted, the ore sizes, as just coming. But the data becomes effectively very powerful, where we are not only looking at what's happening at the belt, but also this gives us indication of every blast that has been gone through from the primary crusher, whether the crusher is performing, like do we have a crusher gap there? So there is another level of changes we can make there, right? From the blasting perspective, that we are not getting there is a lot of crusher gap. So let's go and change and make some decisions on our blast modeling side. There's another example on the crusher side, like, the AI is trained to do an optical flow of analysis for each falling rock here, which predicts the particle size. And it is especially looked to look at the scenarios of not only the crusher gap here, but also as each individual rock particles are moved here, how we can go back and take this data to our blast modeling. So if we can have a data from our pit side, which is how the blast was designed and done, we have the data there. Now we know the geospatial positions of each drilled hole. And if we have a tracker in a form of GPS or a RFID, we know that which material is coming from which geology, and we can track that from the systems which are installed at the crusher. So now we can easily track from the mine to the mill each individual rock particles and how it behaved. So what does that mean? Going back to some of my initial commentary about how the feedback loop works. So if we can use the data from here to go back and say, we used a certain powder factor on specific drilled hole here, what was the depth, what was the geology, if we know. We stemmed this, there was a joint conditions of this type. Now we can correlate this data to essentially the throughput at the plant. So essentially tracking each drilled hole to the mill can give us a good understanding of not only what explosives conditions gave us that output, but also what was the geology there. So if we have certain conditions of, let's say, not controllable from the geology perspective, we know now what to work with in the next blast for that. So we can clearly draw a relationship between mill throughput and powder factor that can result into a really good analysis of daily yield analysis. If we are getting a lot of dry fines or the wet fines, how do we control those? And then applying that data back to the prediction, which means, can we go back and take this data to make some design changes, which we are getting from the mill? Can we, if we are designing, if we are coming up with a new explosives product, how it will perform? Now we have the scenario outcomes, to play with it. So overall, all this data now, we have the structure way of looking at that. We have input variables on loading, drilling, timing, rock mass, and then we have output variables that we want to control. So in this case, if you want to control a fragmentation or a percentage range or a vibration or a cost that we want to control overall, but what other parameters will have an effect or an impact there? So we can get those understanding, and then we can also further use that not only to simulate, but also to see the performance. So we can have like multiple shots that you can, as you get more data, the more data can be utilized to run a better optimization here. And repeating the same workflows, you can start to see what are the outcomes that you're desiring, whether you're meeting those or not. And this AI, all use cases that I kind of went through, the feedback loop with the AI predictions is a key here. So with that, I would like to conclude. Hope it was useful. We have